Hello everyone, this is the continuation of our last video uploaded in YouTube regarding atomic structure for NEET and JEE. Before going to this lecture, please make sure that you have watched all the lectures uploaded in atomic structure in YouTube for atomic structure. Let's continue. Let us see the first question. The energy of second Bohr orbit of the hydrogen atom is minus 328 kilojoule per mole. Hence the energy of the fourth Bohr orbit would be. See, we have the formula related to energy is En. In nth orbit, energy is minus k into z square by n square. Now they are asking about for hydrogen atom. Now hydrogen atom, the atomic number is 1, so z is 1, and it is given that second Bohr orbit, so n equals to 2. Put the values, z equals to 1 and n equals to 2, you will get 1 by 4. So from this you can find out the value of k. K would be 4 into E2, and E2 is given, energy is given minus 328. So you will be you will get minus, and here we have minus k, so minus get cancelled out, so we can find the value of k. Now they are asking hence the energy of the fourth Bohr orbit, so you have to find out the fourth Bohr, E4. So E4, put the value, z equals to 1, n equals to 4, 16. So you know the value of k, put the values, you will get it as minus 82 kilojoule per mole. Second question is, in hydrogen atom, energy of first excited state is, first excited state, that means n equals to 2. Then find out kinetic energy of the same orbit of hydrogen atom. Now see, kinetic energy is our half mv square, and we know v equals to 2 pi e square by n into h. Put the values, 2 square is 4, 4 and 2 cancel out, you will get 2m pi e square by nh whole square. Now total energy we know as En equals to minus 2 pi square m e to the power 4 by n square h square. Now we can formulate this thing as something like this, as kinetic energy as pi e square by nh whole square, and we left with 2 into m. Now see, 2 into m pi e square whole square by n h whole square is our kinetic energy. We have minus sign here, so we got total energy as minus of kinetic energy. And it is given that first excited state energy is minus 3.4 electron volt. So kinetic energy of the same orbit means first excited state, that is n equals to 2, same orbit, we can see that total energy is our minus of kinetic energy. So total energy is given minus 3.4 electron volt, so you have to find the kinetic energy. Now kinetic energy is equals to minus of total energy, minus of En. So our kinetic energy would be minus of minus 3.4, that is plus 3.4 electron volt. That is option A. So let us continue. Question number 3, the hydrogen atom. In hydrogen atom, the de Broglie wavelength of an electron in second Bohr orbit, that is n equals to 2, is so de Broglie wavelength. You need de Broglie wavelength. See, from de Broglie equation we know lambda equals to h by mb, right? This is our de Broglie wavelength. So you need to find the lambda. This is your de Broglie wavelength. Now it is given that Bohr radius A0 as given as 52.9 picometer. Now see, it is in the second Bohr orbit, so n equals to 2, and we know the formula Rn, nth Bohr orbit radius, is n square into A0. So it is n equals to 2, so 2 square into A0, so 4 into 52.9, that is 211.6 picometer. Now we know that in any orbit, angular momentum is nh by 2 pi. Angular momentum in any orbit, angular momentum is nh by 2 pi. So from here we can say that n is our 2, so 2h by 2 pi, that is h by 2 pi, and h equals to 2 pi h by 2 pi, 2 to cancel out, so h equals to mvr into pi, Now put the value here, or otherwise you can say that mv into lambda is equals to h. Now equate these two things, that is h equals to mvr pi and lambda mv. So lambda mv equals to mvr pi, mv cancel out. So you can see that lambda equals to pi into r. Now r is given as 211.6 we have found out. So 211.6 pi. So our option B is correct. Now next question, 4d, 5p, 5f and 6p orbitals are arranged in order of decreasing energy, then the correct option. Now in order to solve this type of question, this is a very common type of question and that may come in your exam frequently. Now see, in order to find out this type of question, you need to find the value of n plus L, that is principal quantum number and azimuthal quantum number. You have to find out the value of principal quantum number plus azimuthal quantum number. Now higher the value of n plus L, higher is the energy. Higher the value of n plus L, higher is the energy. And if two different types of orbitals have same value of n plus L, then you have to find the lower value of n has the lower energy. Let us say, see, we know already that for s orbital L equals to 0, for p orbital L equals to 1, for d orbital L equals to 2, and for f orbital L equals to 3. Now see here 5f, that is 5 plus 3, that is here 8. Now 6 plus 1, that is 7, 5 plus 1, that is 6, and 4 plus d is 2, 4 plus 2, that is 6. Now see, here you have to arrange in decreasing order of energy, that is highest energy. What would be the highest energy? Here 8 is highest, no doubt. Now what is next? Next is 7, right? 7 is the highest because n plus L value is higher. This is highest, this is then higher. Now see, here we have two equal values, right? 6 and 6. So for this n plus L value is same. For n plus L, if n plus L value is same, then you have to find out what is the value of n. For lower value of n, you will have lower energy. See, here n value is 4, here n value is 5. So 4d would have lower energy. So our option would be 5f, 6p, 5p, 4d. Option B is correct. So let us see in our next question, the outer electronic configuration of gadolinium. Now see, gadolinium atomic number is 64. Now in order to write down this configuration, there are exceptions, right? Chromium, copper, all those are exceptions we have learned in our board level lectures. Now in order to solve this type of question, always write this thing: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, go like this. Now 1s would be first, then 2s or singly, then 2p, 3s, then 3p, 4s, then 3d, 4p, 5s, then 4d, 5p, 6s, then 4f, 5d, 6p, and it will go something like this. Now if you want to write it in the full form, then it will be, see, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f7, 5d1. Now why this electronic configuration is exceptional? See, xenon, which have the electronic atomic number as 54, we know the outermost electronic configuration as 4d10, that is 4d10, 5s2, 4d10, 5s2 and 5p6. That's all. See, it is noble gas, so that's why its electronic configuration is fully filled. So you have to remember the last electronic configuration where it has ended. It has ended at 5p6. That means we have to start from 55. In 55 it would be 5p6 as it is, then 6s1, right? For 56 it would be 6s2, right? It is done. Then we have to come forward to 4f7. So 57 would be 4f1, 58 would be 4f2, 59 would be 4f3, then 59 would be 4f3. So see, here I have made a little mistake. 55 is your 6s1, right? 54 is your we have ended in 5p1. then 55 electron will enter in 6s1, then 56 6s2, another electron added, 57 would be 4f1 6s2, 58 would be 4f2 6s2, 59 would be 4f3 6s2, 60 would be 4f4 6s2, then 61 4f5 6s2, 62 would be 4f6 6s2, 63 would be 4f7 6s2. Now see, in 64 electron will not enter in f orbital, it will not be 4f8 6s2, because we can see here that 4f7 is half filled, 4f7 is half filled. So half filled and fully filled is most stable electronic configuration we have discussed in board level lectures. So this is half filled, that's why the next electron will enter in 5d1. The next electron, the very next electron is 63, and 64th electron will enter in 5d1, not in f orbital. Now see why we have arranged 4f7, 5d1 and 6s2. I have written 6s2 in the last, because see, we have discussed in the question number 3 or 4. Please rewind and see the video. Here n is n plus l value, we have to see the n plus l value, right? Here 6 and s is 0, so it will be 6, and here for f, s is 0, p is 1, d is 2, f is 3, so 4 plus 3 is 7, and then 5d, then 5d is 5 plus 2, that is 7, and then we have to see the n values for equal energy level. So here 4 is less and 6 is here 5 is greater than 4. So we have to write down the configuration as 4f7, then 5d1, then 6s2. So our electronic configuration would be 4f7, 5d1, 6s2. That is option B is correct. And there are some exceptional electronic configuration, and gadolinium is one of them. So let us see now. This is an important topic: orbital wave function and probability distribution. This topic I have not taught in board level and in the previous lecture for JEE mains and advanced. This topic is specially for the JEE advanced students, and if they make difficult questions for JEE mains, then this topic may come, but this is specifically for advanced students. Now see, an orbital wave function psi can be written as product of two functions, that is, one is radial function and another is angular function. The radial function is a function of distance only, whereas the angular function is a function of two angles. One is your theta and another is your phi. So psi, that is our orbital function, wave function, can be written as radial wave function and angular wave function. And angular wave function depends on theta and phi, two angles. Theta and phi are spherical coordinates, that is, if you assume that this is a sphere, then theta and phi are the spherical coordinates, and r is the length of the line between origin and the point P. You can see here r is the distance from origin to line, and in origin we have assumed that we have nucleus. This is our nucleus, that is OP. The angle between line OP and z axis is taken as theta, and phi is the angle of projection of this line, if you project this line on xy plane, then that angle would be in xy plane, that angle would be your phi. Now see, complete wave function represents an orbital. This is the complete wave function. This complete wave function will represent your orbital, in which radial part, that is psi of r, depends upon quantum numbers n and l, and suggests the size of the orbital. So that means the radial function depends on the size of the orbital, whereas the angular part, that is psi of theta and phi, depends upon n, l and m. Please be careful here. The radial function, that is psi of r, depends on the quantum numbers n and l, whereas the angular function, wave function, psi of theta comma phi, depends upon three quantum numbers, that is n, l and m, and suggests the shape. So this angular wave function suggests the shape, and this radial part indicates the size of the orbital. So psi of r related to size of the orbital, and psi of theta comma phi indicates the shape of the orbital. See here we have three functions, right? One is psi of r, one is psi of theta, and another is psi of phi. So it is not easy to plot the variation of psi with these three variables, that is r, theta and phi, in a single diagram. Hence we plot different diagrams for angular variation and for radial variation. So this is the complete diagram. This is the position of electron in xyz coordinate. These are 3D coordinate, and we have put the nucleus in the origin, and electron will revolve around the nucleus in various positions. So if r varies, let us say r is here, and if r is this distance, so electron will be much closer to nucleus. If r is there, electron is there, then the radial function, that is the size, right? This depends on size. So if electron moves away from the nucleus, then size will increase. This is obvious, right? Now this angle is 90 degree. So if this is r, then this component along z axis will be r cos theta, and this is the projection of OP in xy plane is your, let us say this is OP prime, and angle is phi, and this is your r sin theta sin cos phi, this x component, and y component would be, the perpendicular component will be r sin theta cos phi. Now we will see this is the projection for r, theta and phi for orbitals. So this is the basic introduction. Now we will move forward to different shapes for s orbital, p orbital, d orbital. So let us see the shape of s orbital. See, there are several ways to visualize the radial variation of ns orbital, that is n with 1, 2, 3. Our first way is to make the three-dimensional picture in which the shading is heaviest where psi square is largest, and lighter where psi square is smaller. So our wave function psi, and if you square it psi square, you will get a spherical shape. So for s orbital, the 3D dimension is as spherical shape. Now for 1s orbital, this is the most probable space of electron where electron can stay in a sphere. So for 1s we have only one sphere. So 1s, that is n equals to 1, and for s orbital we know l equals to 0. That's why see, we have seen in the previous slide that the size of the orbital depends on n and l. Now see, for 2s, n equals to 2 and l is 0 for s orbital. Now we have two spheres, one sphere is here and another sphere is here. Between these two spheres we have a blank space where no electron can be found. That means in this space, in this white region, no electron can be found, or you can say that probability of finding electron is very less here. And for 3s orbital we have three circles, and in between the two circles, that is, this is one and another circle is the last region where electron can be found. So we have two nodes where electron cannot be found. So this is the electron density distribution of 1s, 2s and 3s orbital. If you can draw the 4s orbital also, it will have three nodes where electron cannot be found. The second way, this is our first way of showing the distribution of electron, that is where the electron can lie. And the second way is to plot the wave function as psi 1s, psi 2s, psi 3s and versus the distance. The distance function, the distance from the nucleus. However, psi has no significance here. Please remember, psi has no significance here, and therefore the plots are also meaningless, except that these plots give the sign of the wave function. These plots give the sign of the wave function. See, for 1s orbital, the shape, the curve look like this. That is the variation of electron with the distance, and as it is in the upper side, this is the curve between psi of r and r. That is, psi is the function of distance. That is, this is the radial plot of our curve. So this is plus, And for 2s orbital, see, this is the same graph psi s versus r, but we have the graph something like this. We have the graph something like this. That is, we have for 2s orbital we have plus and minus sign. That is, in between plus and minus, where the electron cross x axis, you will have a node here. That's why see, we have a one node here. That is, this is a blank space where electron cannot be found, or electron, the probability of finding electron is very less here. And if you plot the 3s orbital, then the psi r versus r curve will look like this, 2 positive, and here in the negative x axis and negative y axis it will be minus. So here you can see that we crossed, the curve crosses twice in the x axis. That is, we have two nodes. That means in 3s orbital, here also you can see one node, two nodes. So in 3s orbital we have two nodes where electron cannot be found. So let us see the third way of plotting electron density from the nucleus. Third way is to plot square of the wave function. See, if you notice the last slide, in the last curves, we have seen that we can plot the graph between psi of r versus r. But here we are plotting, the only main difference is here we are plotting with psi square with r. The square of the wave function, psi square, is the average electron density at some particular point in space at a distance r from the nucleus. Psi square is the measure of probability of finding the electron in a unit volume around a particular point, is called radial probability density, and the graph psi square against the function of distance r from the nucleus are called probability distribution curves. So these are your actually probability distribution curves. Psi square versus r curves are known as probability distribution curves. The three-dimensional region of space around the nucleus where the probability for finding the electron is maximum is called your orbital. Okay, now we know the concept of orbital. In the last two figures reveal that boundary surface of psi square and psi. In the last figure we have seen the curve between psi and r. This is the curve. And in the next curve we have seen something like this. And the third curve we have seen something like this. Two curves. Okay, two curves. So from this we can say that the only difference is here psi square is positive, so make this positive. So first curve would be same for 1s. In the second curve, see, here we have negative region. So if we make it square, then negative region would be positive. So that's why our negative part comes in the upper part. Negative part comes in the upper part. That is the only difference. Here also it touches x-axis at one point, so we have one node. Here it touches one point, so we have one node here. And in the second curve, if you see, we have this negative part. This negative part would be positive. This negative part would be positive, and this positive lies as it is. So this is our 3s orbital curves. So in 2s and 3s it touches one time and two times, so we have two nodes and one node. This is the only difference between psi square r and psi r. In the psi r we have negative and positive region. Here we have only positive region. Let us continue the fourth way of representing radial. Fourth way is the plot of radial density function. That is, radial density function is your 4 pi r square psi square versus r. So this is the radial density function for 2s, 1s and 2s orbital. This is the curve, okay, and this is the radial density function 4 pi r square psi square. The radial density, the psi square for an orbital, gives the probable density of finding the electron at a distance r from the nucleus. Since the atom has spherical symmetry for 1s, 2s, 3s, the probability of finding electron is better to consider between the spheres of r plus dr and r. So how this thing came? They see the volume of the shell. If we take r and r plus r dr, that is see, if we take this thing where to show, if we take this radius, let us say this is the sphere of radius r and this is the sphere of radius r plus dr. Okay, this is the outer sphere is r plus dr. So the volume would be, this volume would be this volume, the middle one is 4/3 pi r plus dr whole cube minus 4/3 pi r cube. So this will come out to be after binomial approximation from here, because dr is small, so dr cube will also be very small. So we can ignore, after approximation we can say that this thing will comes up to be 4 pi r square dr. Thus radial probability given by this thing 4 pi r square psi square dr is independent of, and remember this direction is independent of direction, and thus radial probability function 4 pi r square psi square gives the probability of finding electron. This do not give any direction, this only gives finding of electron, where the electron can lie at from the nucleus at a distance r from the nucleus regardless of the direction. So from Schrodinger wave equation and from this psi square or psi, we cannot find any direction, we can only find where it can stay. So for p orbital, the plot of psi square and probability density function 4 pi r square psi square for 2p orbital versus r, these are the psi versus r curve, and for 2p orbital psi square versus r curve is something like this, and for probability density function 4 pi r square psi square versus r curve looks something like this. Now if you compare this curve for 2s orbital psi square versus r curve, and for 2p orbital psi square versus r curve, 2s and 2p reveals that maximum probability for 2p is at a slightly lesser distance than 2s. Also 2s orbitals show small additional maxima than the maxima of small additional maxima. See, we have two maxima here, one is here and another something loop here. So we have two maxima here, small additional maxima of 2p orbital. This reveals that electron in 2s orbital spends some of its time near the nucleus, and therefore 2s orbital electron are held more tightly than 2p orbital electron. Or finally we can conclude from this curve and this curve that 2s energy level is lower than 2p energy level. You can clearly see that the curve is more upward than this curve, that is maxima is highest here, maxima is lower here. So that means from this curve we can conclude that electron spends more time in 2s orbital than 2p orbital, that is electron lies more closely to nucleus in 2s orbital, and from this curve we can say the curve is, the maximum is in further distance. So our 2p electron will lie further than in 2p orbital from nucleus. So finally we can conclude that the energy of 2s orbital is lower than 2p orbital. That's all you can conclude from this graphical representation, and now we will move forward to our next topic. So let us continue. See, we have already discussed the shape of s orbital, p orbital, d orbital. In d orbital, in p orbital we know that it is px, py, pz, and d orbital we have 5 shapes, right? That is dxy, dyz, dzx, dz square, and dx square minus y square. But here see, in f orbital we have 7 shapes, namely f of y x square minus y square, y z square minus x square, x z square minus y square, x square minus y square, z x square minus y square, and f of z x square minus z square, and f x y z. These f orbital shapes are not in your syllabus, but just remember these names of these orbitals. So let us continue in next topic, that is magnetic properties. In magnetic properties we have paramagnetic, diamagnetic, and ferromagnetic. Paramagnetic are those substances or molecules or ions that those have unpaired electrons. This is extremely important. The more it has unpaired electron, the more the paramagnetic nature will be. Example, sodium is a paramagnetic material. So they lose there, but here one thing is you have to notice that they lose their magnetism when removed from magnetic field. In diamagnetism, we have substances whose molecules, ions and atoms have no unpaired electrons. It has unpaired electrons in paramagnetic properties. In diamagnetic properties, we don't have unpaired electrons. Example, NaCl and NO2. We will see the shapes and diagrams of this NO2 and NaCl in molecular bonding. In ferromagnetism, molecules or atoms in solid state attracted in magnetic field as well as retaining the magnetic property. This is very important. In paramagnetism, if we have unpaired electrons, for that unpaired electrons, the paramagnetic molecules will attract to magnetic field. But if we remove the magnetic field, the paramagnetism, the magnetic property will be vanished. But here in ferromagnetic material, the magnetic property will be retained. Okay, and the example is iron, and it cannot be observed in solution state. It can be observed only in solid state. It cannot be observed, that is ferromagnetic property cannot be observed in solution state. Now by this we have completed all the theory related to JEE Mains Advanced board level. Please kindly go through our previous lectures for atomic structures uploaded in YouTube. I hope these videos are making you interest into chemistry. Now we will see some problems related to atomic structure for JEE Mains and Advanced. So let us see one question. In a certain electronic transition from quantum level n to the ground state in atomic hydrogen, in one or more states, no line belonging to bracket series is observed. What wave number may be observed in the Balmer series? So this is a very important question. See here, it is given that no line is found in bracket series. So we have Lehman, then Balmer, then Paschen, then bracket. So that means bracket is for n equals to 4 quantum number, right? This is n equals to 1, n equals to 2, n equals to 3 quantum number. No line is found in bracket series. So n cannot be greater than 4. So n must be 4. N must be equal to 4. Otherwise, if n greater than 4, then bracket series will also be noticed. So that's number of lines. So that's number of lines found is summation of delta n, that is n2 minus n1, that is n is 4, that is n is 4. So from 4 to it can jump from ground state, that is 4 to 1, that is 4 minus 1. This is summation of 3, that means 3 plus 2 plus 1, that is we can see 6 lines. Those 6 lines can be, the electron can jump from 4 to 3, 4 to 2, 4 to 1, 3 to 2, 3 to 1 and 2 to 1. That is, these 6 lines can be found out. Now out of these 6 lines, see, they want only Balmer series. So Balmer series is for n equals to 2. That means wherever electron jumps from n equals to 4 to 2, and here n equals to 3 to 2. In these two cases we can find out the Balmer series. So we know nu bar equals to 1 by lambda RH, 1 by n1 square minus 1 by n2 square. From where to where, the last one, from where it jumps, from where to where, that is it jumps from 4 to 2, that is here we will have 1 by 2 square minus 1 by 4 square, you will calculate, you will get 3 by 16 RH. And in the second case, n equals to 3 and n equals to 2, so we have 1 by 2 square minus 1 by 3 square, calculate, we will have 5 by 36 RH. So our option C is correct. So let us see another question. When photons of energy 4.25 electron volt strikes the surface of a metal A, the ejected photoelectrons have maximum kinetic energy Ta in electron volt and de Broglie wavelength lambda A. The maximum kinetic energy of photoelectrons liberated from another metal surface B by photons of energy 4.70 electron volts is, this relation is given, TB equals to Ta minus 1.50 electron volt. If the de Broglie wavelength of these photoelectrons is lambda B equals to twice lambda A, then which of the relation is correct? Now let us see, this is an important question. So we know that whenever if there is a metal surface and light of wavelength equals to h nu strikes the surface, some energy is given to the electron to knock it off from the outer orbital and come into the surface, and rest of the energy goes to its to give it to kinetic energy, that is half mv square. So from this we can say that E equals to your work function plus this kinetic energy. So from this is our basic relation, right? So energy. So let us say here two metal surfaces A and B, and let us say the work function of each of the metal surface is WA and WB. This work function can be written as E equals to h nu, and E is h nu, right? E is h nu and work function is h nu naught plus kinetic energy. So every metal surface has its own work function, because if you change the wavelength, if you change the frequency of the light or wavelength of the light coming, then your work function will change. Work function is, see, this is the minimum frequency required to eject an electron from the metal surface. So from this we can say that our energy, first relation is given that for the metal surface A, the energy is 4.25 electron volt. That is, the energy which is coming is 4.25 electron volt. That must be equals to our work function plus kinetic energy. Here kinetic energy is represented as TA. Now TA should be 4.25 minus WA, and TB is given, see, the energy of the work function is given as 4.70. So TB should be our 4.70 minus our work function, and the energy is given as 4.70. So 4.70 equals to WB plus TA. Now TB would be 4.70 minus WB. Here we got two relations. Now subtract TB minus TA. So TB is given as this, TA is this. So after simplification you will get 0.45 WA minus WB. Now take everything in one side. See, here one relation is given, TB equals to TA minus 1.50. So TB equals to TA minus 1.50 minus TA. Now this TA cancel out, and we will get minus 1.50, and from right hand side take everything, take 0.45 to left hand side. So minus 1.050 minus 0.5 is WA minus WB. So after calculation you will get minus 1.95 as WA minus WB. So take minus common, you will get WB minus WA as 1.95. Now see, de Broglie wavelength, we know lambda equals to h by mv. Here we have written mu, the same thing. Now we know that kinetic energy is half mu square, so u would be root under 2ke by m. Root under 2ke by m. Put here, take the m into a square root, that would be m square, m cancel out. So we will get h by root under 2ke into m. So from here, see, this is Planck constant is constant, mass of the electron is constant, 2 is constant. So from here we can say that lambda is inversely proportional to your kinetic energy. So lambda b by lambda a should be equals to kinetic energy of A by kinetic energy of B. Now see, here one relation is given, lambda b by lambda is 2. So lambda b by lambda, this value is 2. So square, do square. So you will get kinetic energy of A by kinetic energy of B as 4. And here kinetic energy is represented as TA and TB. So this kinetic energy of A by B should be TA by TB. Now TB is given as TA minus 1.5. So TB is this is your TA minus 1.5. Now simplify, you will get TA as 2 electron volt. Now if you got TA, now this, from this relation put TA equals to 2 minus 1.5, that is 0.5 electron volt. Once you got TA and TB, you can get W. From this relation you will get WA and WB. So which of the option is correct? TB is 0.5 electron volt is correct. TA is 2 electron volt is correct. But our C, which is not correct, we have to find which is not correct. This is your correct. The answer to the answer it is correct. We have to find out which is not correct. The work function of the B is 1.20. Work function of B is 4.2. So our answer would be this. This is the incorrect answer. And the work function of A is 2.25. Work function of A is 2.25. That means A, C, D are correct option, and which is not correct, option B is not correct. So let us continue. The ratio of the de Broglie. So see the ratio of the de Broglie wavelength of molecules of hydrogen and helium at 27 degrees Celsius and 127 degrees Celsius respectively is. So see, lambda equals to H by md we already know. You have to remember that U is our root under 3 RT by m, where R is your gas constant and T is temperature. So this would be H by m hydrogen, root under of 3 R, let us say this is temperature 1, and m hydrogen. And in the same manner, lambda helium would be H by m helium into root under 3 R T by m helium. So divide lambda hydrogen by lambda helium, all the terms will go out, and you will only have T2 into mhe by T1 into mh2. And put mh2 inside, so it will be mh2 whole square, mh2 will be cancelled out. So you can remember this formula as something like this, that is lambda equals to H by root under 3 R T m. You can remember this formula for wavelength. Okay, so you can see here will get cancelled out, T2 by T1, mhe by m hydrogen. Put the values. T2 temperature is 127 degrees Celsius, so you have to for gas you have to convert it into Kelvin, so it will be 400 Kelvin, and T1 is 27 degrees Celsius, so it will be 300 Kelvin. And see, mass of helium is twice the mass of hydrogen, right? So you can 4, you don't have to put it here actually, 4 by 2. So mass of helium is twice the mass of hydrogen. So 4, you will get it as 1.633. That is option A. Now next question, P is the probability of finding the 1s electron of hydrogen atom is a spherical shell of infinitesimal thickness dr at a distance r from the nucleus. The volume of this shell is 4 pi r square dr. See, from this you can see that the sketch would be from probability distribution function. The last slide we have learned in the theory, the qualitative sketch of the dependence of P on r, that is 4 pi square r psi square by r distance. So probability of finding 1s electron would be, the graph would be option D. We have just completed the theory. Let's go through the theory. You'll understand that for 1s orbital, 4 pi r square psi square versus r graph is actually your option D. So by this we have completed atomic structure. I will try to upload more questions, previous year questions, if we got at least 200 likes. So please like, share and subscribe. Thank you. All the best.